This example is from MGF 1107, section 10.2, when dealing with groups. This is problem 34. It says, let E and O represent even numbers and odd numbers respectively. Complete the table for the operation of multiplication. So in this example, we do not have specific even and odd numbers. We're making a generalization for all even and odd numbers. Part B says, determine whether the mathematical system forms a commutative group under the operation of multiplication. Explain your answer. Well, let's first fill out the table. In order to fill out the table, we have to multiply, in general terms, an even times an even. Well, when we multiply an even number times another even number, that will always be even, such as 8 times 6 is 48, 10 times 6 is 60. We're always going to result in an even. So even times even is even. Even times odd. Any even number times any odd number will also be even. Whenever you multiply an even number times an even or an odd, you are going to get an even number. So even times an odd would be like 8 times 7 or 4 times 9, and those results of those products will be even numbers. So the first row will be even, even. Now in the second row, when we multiply an odd times an even, what we just discussed, when we multiply an odd times an even, that will be an even, such as 7 times 8 is 56, which is even. But an odd times an odd, like 7 times 7, 3 times 3, 3 times 7, 11 times 3, those answers will be odd. So the second row will be even, odd. So that is our mathematical system. It has two elements, even and odd, and the operation is multiplication. Now we have to determine whether that mathematical system that has two elements under the operation of multiplication is a commutative group. So we're going to determine whether it's a group, and then on top of that we have to determine whether it's commutative. Now recall, in order for it to be a group, for that mathematical system to be a group, there are 4 requirements, and those are: the elements must be closed, which means we do not get any new elements when we perform the operation, and an identity must exist, which means when we perform that operation with a value, we get back the original element. Every element in the set has an inverse under the given operation. That means each element has another element, which could be the same element, which when performed will give you back to the identity element. And the set of elements is associative under the given operation of multiplication. Now once it meets those 4 conditions, then we can learn whether it is commutative. Thus, if it meets all 4 requirements and is commutative, then it's a commutative group. So requirement number 1 is whether it's closed, the system is closed. And one thing you notice when we perform the operation, even times odd times even, odd times odd, our results, the 4 in the body of the table, O, are all elements of the original set. Thus, it is closed. We do not get additional elements. So the results stay within the set of elements we began with. Thus, it is closed. And an identity element exists for the set. So we only have 2 elements in the set, even and odd, E and O. So let's see if one of those is an identity element. Well, if you look at the first row, you can see that E times E is E, but E times O is E, which means when we go E times odd, even times odd, we get even back. Thus, even is not the identity element since it did not give us what we started with back. But if you notice, odd times even is even, and odd times odd is odd. So if you look at this row, that is in the same order as the elements that we started with, which means odd is the identity element. It did not change the original set of elements. And you can see that also in a vertical format. If you look at odd here, even times odd is even, and odd times odd is odd. These elements are in the same order as the original elements. That means the identity element will be odd numbers. They take you back to where you started. In other words, they didn't change the value of the element. So let me erase that. The third requirement is every element, which means the two elements. We only have even and odd, so every element just means the two. In the set has an inverse under the given operation. Okay, so if we have an element and we perform the operation with its inverse, we have to get back to the identity element of odd. Well, if you look at the element even, its inverse will be that element that will take us back to the identity element of O or odd. But even times even is even, and even times odd is even. So even does not have an inverse, because none of these results here would give us the identity element of odd. So does every element have an inverse? No, even doesn't have an inverse. One thing you should notice is odd, when it's performed with even is even, so that means even is not odd's inverse, but odd times odd will get you back to the identity element of odd, which means odd is its own inverse. But even numbers in this system do not have an inverse, because both of the results would give us even and not the identity element. So this condition is not met, thus it is not a group. Thus, if it's not a group, it cannot be a commutative group. So we know the answer is no, but we have to make sure we come up with the right justification. So A is no, the set of elements is not associative under the operation of multiplication. Well, that's not the reason we said. We said it's because not every element had an inverse. No, there's no identity element. Well, we did say there was an identity element. It's odd, so that's not true. No, the set of elements is not closed. Well, it is closed, so that's not the right value. Yes, it meets all 5 requirements needed for a mathematical system to be called a commutative group. That's not true, because it doesn't meet all 4 plus the 1 requirement. No, there is at least one element that does not have an inverse under the operation of multiplication. That's correct. We said the element of even did not have an inverse. So that's why E is checked. No, the set of elements is not commutative under the operation of multiplication. That's not the reason that it's not a commutative group. So the correct answer is E.